Physics students, good afternoon. Mr. Fugit here. In this video today, we're going to be looking at a few of the problems on your review for test number 1, which covers over units 0 on density and unit 1 on vectors. So here specifically, we're going to be looking at problems number 19 and 20. So I'll go ahead and jump right in. And remember that copies of your review, as well as the key for the review, are located on Canvas in the unit 0 and unit 1 page. So question 19 says this. Define vector C such that C is equal to A plus B. So we're saying that vector C is equal to vector A plus vector B. As we get a few extra marks in here. Okay, so here's what we're given. Vector A is 7 units at an angle of 45 degrees. And vector B, let me write these just so they're a little bit more descriptive for us. Vector B is 2 units at 20 degrees. And now because that's a little small, I'm going to draw that a little bit bigger. Now we're going to analyze these in a way where we draw them a little bit larger, but you kind of get the idea for right now. So I can actually scale this up a little bit. There we go. And vector B. There we go. Okay, so we have vector A and vector B. Now obviously 7 should be longer than 2, but just so the 2 is not really small, we can see it well, and I'm just going to draw it here. So these are not drawn perfectly to scale. So we want to define vector C such that we add A to B. Here's the issue. Vector A and vector B are not in the same direction. They're both going up and to the right, but they're not in the same direction. And we cannot add vectors unless they're in the same direction. But here's something that we can identify. Vector A is partially in the x, and it's partially in the y direction. It's to the right and up. And vector B is similar to that. It is partially in the x and partially in the y direction. So in order to figure out how to add these together, we cannot just add 7 and 2, because 7 and 2 are not in the same direction. But we can add the values that are in the same direction. The x value here to the x value here, y value to y value. So we need to, before we add anything, we actually have to break these vectors down into their components or their parts. So we're going to start with vector A. To find the x component, that means it is adjacent. We know our hypotenuse. So adjacent and hypotenuse means we need to use cosine. So cosine of 45 is x over 7. I'm going to work through this a little quick. So to get 7 to the other side of our equation, so we can get x by itself, I've got to multiply by 7 in our numerator. So 7 over 7, those values cancel out, and we're left with x is equal to 7 cosine of 45 degrees. Okay, so I'll go ahead and plug that into my calculator, making sure I'm in degree mode, not radian mode. So 7 cosine 45 gives me a value for x, about 4.949. So we'll go 4.95. Now, because we have a 45 degree angle here, that should give us a clue that can save us some time. Because our angle is 45 degrees, that means our x and y components will be equal. I could go ahead and plug in 7 sine of 45, sine because the y side is opposite related to our hypotenuse. So 7 sine 45, if you want to double check, should give you the same value, 4.95. So now we know that the x component and the y component are 4.95. This will only be true if it equals 45 degrees, which in this case it is. So we know our components for vector A. Now we need to do the same for vector B. Unfortunately, our angle is not 45 degrees, so we'll have to do a little bit more work here. So same approach, need to find the x component. We'll use cosine. So cosine of our angle, 20 degrees, is equal to the adjacent side, which is x, over our hypotenuse 2. So to get x by itself, I'll just multiply by 2 in the numerator. So 2 divided by 2, those cancel out. I'm left with x is equal to 2 cosine 20 degrees. So we'll plug this in, 2 cosine 20, and we'll get a value of 1.88. Okay, so I'll plug that in here, 1.88. Okay, now we need to find the y component. We can't use cosine anymore because cosine relates adjacent to hypotenuse. We need a function for the opposite side of our hypotenuse. That would be a sine function. So our expression here looks like this. Sine of our angle, 20 degrees, is equal to y, our adjacent side, divided by our hypotenuse. Now we need to get y by itself, so just like before, I'll multiply by 2, left side and right hand side. So 2 over 2, those values will cancel out. And now we'll be left with y is equal to 2 sine of 20 degrees. So you'll notice a very, very similar approach. The only thing that's changing here is we're using a different trig function. So 2 sine of 20 degrees gives us about 0.684. Okay, so we know our components. X and y for triangle or for vector A, and x and y. I'm not going to write that here because it's a little bit crowded. Let's see if I can maybe this a little bit. Just 0.684. There we go. Okay. Now we cannot, as I mentioned before, just add 9 and 2. But we can add the parts of our triangles that are similar, the x parts or x components, and the y parts or y components. So now I'm going to do that. I'm going to add a sub x and b sub x. That's going to give me 4.95 plus 1.88. And remember, we said that when we add a and b, the result should be c. But here we're just looking at the x component or the x part. So 4.95 plus 1.88 gives us approximately 6.83. That would be the x component of our overall answer, vector c. And then we have a sub y, we'll add the values that are in the same direction, plus b sub y, and that should equal c sub y. Ooh, come on, there we go. So now I'm just going to add my values for the y direction. So a sub y was 4.95, b sub y was a small value, 0.684. We'll add those together. So 4.95 plus 0.684, we end up getting 5.637, dropping around to 5.64. So now, what we've done here is we've now added our vectors in parts or components. Excuse me, which is actually the correct way to do this. So we've broken our vectors into their components, we've added the similar components, and now we're going to redraw our final picture. So I know that my x component for C should be this, 6.83. My y component should be this, 5.64. So now I'm going to take those and draw them out. C sub x, 6.83. There we go. C sub y, 5.64. And using those components will help us find our overall vector C. So how do we do that? Well, we know two sides of a right triangle here. That should tell us we're going to use Pythagorean theorem. So we'll take our two sides. A squared plus b squared is equal to c squared. Again, don't let all the notation confuse you. A here would just be one of our sides. B, another one of our sides. C is our hypotenuse, which is what we're looking for. But it's just a way of identifying which side goes in which place in our equation. So A, we have 6.83. We'll just say it's the x component squared plus B, which was 5.64, 5.74, 64 squared is equal to C squared. So we'll plug our values in. 6 6.83 squared plus 5.64 squared. We get a value of about 78.5. So 78.5 is equal to c squared. And then to find our value c, which is just our hypotenuse, we'll take the square root. And that should give us approximately 8.86. So our hypotenuse, c overall, should be 8.86 units. Which should make sense given the numbers that we have, because that value is greater than both the base and the height of our triangle. Okay? So now we're able to solve for what is vector c. And the way that we did that was by breaking our vectors into their parts, the x part and the y part, and then adding the similar parts. Once we had those, we could then draw our final vector, c, because we knew its parts, x and y. Okay, so the last thing we'll do here is find our angle, because when we want to find a vector, we need the magnitude, how long the vector is, and its direction. That would be the angle. So here we can really use any function that we want. I tend to default to using tangent, but really because we know all three sides, we could do whatever we wanted to. So tangent of our angle theta is equal to the opposite side, which would be, I believe, c sub y, over the adjacent side, which is c sub x. So tangent of our angle theta is going to be 5.64 divided by 6.83. Okay, so we plugged in what we know, but now we need to get theta by itself, which means we have to get rid of the tangent function. So we'll take inverse tan on both sides of our equation. Tangent multiplied by inverse tangent, those will cancel out. We'll be left with an expression for theta, because our tangents are now gone. That is equal to the inverse tangent of 5.64 divided by 6.83. Okay, so here we go. Inverse tangent, 5.64 over 6.83. Again, making sure we're in degree mode, we should get approximately about 39.5 degrees. Okay. So we end up getting a value for theta. It's right about 39 degrees. A little bit of rounding that we did in here, but it should be right about 39. My key says about 37.8. We did do a little bit of rounding in here, so we should be right about that value. Okay, 38 degrees to 39 degrees, those would be the same answer. Okay, in terms of what we're looking for, they're very similar. Okay? So this is what we would look for if we were trying to solve for a resultant vector. We draw our vectors out, we break down our vectors into their components, we add the similar components, and then we redraw our final picture to find the magnitude, our hypotenuse, and the direction, which would be our angle. Okay? So this involves all the skills we're looking for when dealing with vectors. Breaking down into components, adding similar components, and using our skills of trigonometry that involve a Pythagorean theorem and a trig function. Okay, now lastly, the final problem on your review says this. Define vector t such that t equals r plus s. So here, number 20, we're told vector t equals vector r plus vector s. Now looking at your picture, here's what we know. Vector r now looks like this. It is 3 units to the right. Vector s is 4 units straight down. So what we can do is we can actually draw these out, and in doing so, that will give us a much better picture of what's going on. So because neither of these vectors are in the same direction, we have to draw them what we call tail to tip. So here's what I'm going to do. Vector r, okay, because we're adding r to s, I'm going to move here to the middle. Vector s, I'm going to add that to the end of vector r. So something like this. And I'm going to move this s to the other side. S equals 4. Now typically, we've talked about the way we add vectors is by breaking them into their components. But these vectors don't really have components because they're only in one direction. So we're told t, vector t, is the result of adding r and s. So that means t would be equal to r plus s, which would land me down here. So this would be vector t. So if you'll notice, we can model this as a right triangle, and we should be able to determine, well, vector t is actually going to be part of a Pythagorean triple. 3, 4, t should be equal to 5. Write this out here a little bit more cleanly. So vector t should be equal to 5. Now, if we're a little bit unsure how did you get there, I don't necessarily remember that it's a Pythagorean triple. Here's what I would do. We would say that a squared plus, it's just in black, a squared plus b squared equals c squared. So a and b are just going to be the two sides of our triangle that are not our hypotenuse. We don't really care which one is which for what we're doing here. So we'll say a is 3 squared plus 4 squared is equal to c squared. So 3 squared gives us 9, plus 4 squared gives us 16. 9 and 16 gives us 25. Remember, this is equal to c squared. And the square root of 25 gives us a value of 5. C just being our hypotenuse, which is vector t. So again, there's the proof so that we know this is actually a value of 5. So we know our magnitude, which is one part of finding a vector. Now we need our direction, which is going to be our angle. So, well, here we can really use any function that we want, any tangent, sine, cosine, because we know all of our sides. As I mentioned before, my typical default is tangent. So I'll go with tangent of our angle, theta, is equal to, well, opposite. So opposite of our angle is side 4. Adjacent is side 3. So now we want to get theta by itself, which as we've seen, we multiply by the inverse of tangent. Inverse tangent. So tangent multiplied by inverse tangent, those will cancel out. And we'll have a value for theta that is equal to the inverse tangent of 4 over 3. Okay, so to finish this out, we will plug in inverse tangent, which will hit second tan, 4 over 3. And we should get a value for theta of approximately 53.1 degrees. Now, something we've discussed in class is how to make sure we're in the right quadrant. So here, from where we start, we go to the right and down. So I want you to think about our coordinate plane here. Right, 0, 90 is straight up vertically. To the left is 180. This is 270. So if we start at the origin, we go to the right, and then we go down. That's going to tell us we're in quadrant number 4, which means our angle shouldn't actually be 53.1 degrees. It's just 53.1 degrees relative to straight east or to the right. So here, there are a few things that we can do. We know that this is 0 or 360. So we can take our value and we can say that this is 360 degrees. And because we are rotating back, or we're going down from our reference point to hit our vector, this is t right here. We can subtract 53.1 from 360. And that would give us a value of about 200, let's see. About 306.9 degrees. That would be a better way of representing our angle so that it's in the right quadrant. We can also say that this is 0 minus 53.1 degrees, so that our angle is negative 53.1 degrees, or just 53.1 degrees back or clockwise from 0. So to finish this out, we would say that vector t is a magnitude of 5 units at an angle of either 306.9 or negative 53.1. So t is equal to 5, we would just say 5 units. We don't really know what the units are, but 5 something, 5 units. at 306.9 degrees. Or we could say negative 53.1. Either of those would be appropriate ways to represent our answer. So here, we're using our components to find our resultant vector, and then we'll use what we know about trigonometry to be able to determine our angle. So hopefully this gets us feeling more comfortable about dealing with some of the concepts of vectors we've been covering in class. If you have any questions, don't hesitate to ask. Good luck.